mainly the idea of this thing. This integral of a loop, we just looked at it, becoming that part a 2 pi I over residues of k going from 1 through n. Right? Residues of this thing with a function f of z in there. They realize that if they control nicely about this residue, they can actually realize they can answer the questions of this type. K going from 0 to infinity, 0 to n of 1 over n squared plus 1. This is like the beginning of a sequence and series. I'm not sure if you know the answer to this one or not, but it is usually introduced. Show this converges, and there's an integral test and comparison test and all that in Calc 2, right? And this is definitely one of the examples you go through in convergence, but they never calculate what this value is, right? And it is not easy to calculate this value. So they looked at the right function. They looked at it, play around. Then they play with the e to the iz. They play with the sine z and cosine z, not just the rational function. They play the technique I've showed you with all the other elementary function. That was just the rational function we looked at it, right? Why not throw in some e to the iz? Why not throw in some sine z? They discover a whole lot of things. They realized that looking at the sine z and cosine z, they could control the poles, and then they can pull out this type of expression. Okay, so skipping that motivation, and they looked at this trigonometric example. They found the following: the pi is just to clear the coefficient. The pi is always around, so they did, by multiplying pi, they realized they can get rid of some of the coefficient there and get to this pure shape. There was no pi in there, right? So next thing they look at it is the cosine pi z and sine pi z. Cosine pi z is analytic. Sine pi z is analytic, right? So where's the poles kicking in? The zeros of a sine pi z, right? What is the zeros of the sine pi z? Is a 0, plus minus 1, plus minus 2, plus minus 3. Those are the zeros. That's why they throw in pi in there, so that the poles are the natural numbers and negative natural numbers, so that they enter the residue of this type of thing. Okay, so if you just do that, and it's going to be just sum over simple natural numbers. So they wanted to control. If you multiply some f of z in there, then it's going to pick up whatever that f of z form is in there like that. So this is the main motivation. They looked at play with the trigonometric function versus this f of z, and together they realized that if you look at this function and put a nice condition on f of z, then the residues of this one is going to be something like this. It's just total magic. All right? So for that one, the key thing is that, all right, let's look at this integral over something called the Cn. It's a pi times a cosine pi z sine pi z. And this function that we're going to choose is this function that we're looking at it here. Is 1 over z squared plus 1 and dz. Another peculiar thing is that this integral, the Cn thing, has to be very, very careful. So what they show is that there is apparently poles in there, right? Poles are 0 and 1 and negative 1, and we just discussed it in here. New poles are kicking in here, right? And they're different. It's I and negative I, right? So they have to put this, but this one is negative n, this one is a positive n. Is this a pole of this function? Yes, right? So they wanted to avoid that pole. To the next one, here's a negative n, negative 1. To the right is positive n plus 1. They wanted to avoid that, and they wanted to control this cosine z, sine z very nicely. To control this cosine z very nicely, you don't want to do a loop integral. You want to do straight integral like this. Then you have a very, very good control on what happened to the sine z and cosine z. Okay? If it's a polynomial, if you do a loop integral, it controls nicely so that you can take it down to 0 or something like that. And you close it up with a square form. And you hit right in the middle in here, avoiding the pole in there. then they realize that they have a very, very good control on this thing, and this becomes 0. As we increase the Cn in this form, skipping the pole, bigger square, and bigger square, by analyzing this part in there, they realize that this goes to 0. This time, it requires a degree is less than, the difference of degree is at least 2. Again, you have to have that condition. Degree of this numerator and denominator is at least 2, and this one, as we put the square around, this whole thing becomes 0. Okay? Then they carefully look at what are the poles and what is the residues. So I'm going to write down, these are all simple poles. You see that? There's simple poles of this one, because the derivative of sine is cosine. That cosine will never be 0 in here. That's one of the homework problem in there. If it's simple 0 down there, it's a simple pole. And additional zeros, the poles are here. It's a +1, +i, and -i, right? So that's what happens is that this Cn thing is eventually is going to approach 0, right? Is a poles adhere. There are these poles and 2 other poles, all right? So if you plug in poles in here and do the what is it? L'Hopital's rule for the quotient rule, the derivative quotient. Turns out this one behaves just like this, k going from -n to +n. These are the poles you plug in here and apply L'Hopital's rule just to that part to get the limit value. And you plug in the rest of the part in here. Z equals k is the pole here, right? These are the poles. You plug in the pole here. We're going to do some calculation here using L'Hopital's rule. And this one is very fine, and there's none of them 0. You plug in that pole in there, and it picks up that pole. And they chose this form so that when you calculate the pole's residue in here, it becomes 1. If you actually calculate the residue to this part, it's 1. And pole is k, z equals k here. Plug it in there, you pick this one up. And there are 2 more poles, right? What are the 2 more poles? Poles coming from this bottom in here. Poles coming from this guy, right? What are the 2 poles there? Plus minus I. So you plug in there, plus minus I. So what is the pole in there? You plug in cosine pi I, right? Sine pi I. And when you do the residue calculation, you multiply z plus I, z minus I, right? So we did that before. So it turns out z plus I, where z is positive I. Z minus I is cancelled, it's simple pole, right? And the other one, pi cosine, this time it's negative I, so isn't that a negative pi I there? Sine negative pi I. This time z plus I is multiplied, so z minus I survives, and you plug in z equals negative I. We've done that before. And this is odd function, and then cancel all that because it gives you that interesting part. Plus these 2 things are exactly the same. Negative cancels here. All right? So 2 copies, and turns out a plus pi divided by I is 2i, it's negative 2i, but they cancel. It becomes a cosine pi I sine pi I. Okay? Now, as n approaches infinity, what happened to the whole thing? It is this whole thing we're calculating, right? Where did they go? In the 0. So we know it's approaching 0. From that, we conclude this one approaches what number? Negative of that guy, right? Agree? Fantastic. Negative of that guy. Now, remember the definition of cosine? You have to take the final exam, so it's time to recall the definition of sine z. Who remembers cosine z? E to the I z, that's right, that thing. All right? So you plug it in there, and you can calculate it. And what happens is that pi times e to the pi I negative pi, e to the pi negative pi I. Thinking about the structure of the definition of sine and cosine, you can kind of imagine that looks just like that. Makes sense, right? And that's the answer. That motivational problem everybody encounters in a Calc 2, why this thing converges, and it's this one. The book also shows you the technique, exactly doing the same technique, just varying one coefficient, which is this one in here. You easily enter this famous result. Proved first by the famous mathematician. Do you know who proved this result? Euler. He proved that it's pi squared over 6, right? All you have to do is just play with this one. The physicists like to call this method its perturbation method. And here you stick one number in there to perturb that one to see how this behaves. Using that technique, you can show that this you replace with a constant a, and how this result varies as a is approaching 0, and then you can get this result. Probably this is your first rigorous proof that you encounter. This one is actually pi squared over 6. Euler proved this. As far as I know, Euler was nobody before he proved this single line result. After he proved this result, he became the biggest star at that period of time, and he remained the biggest star in the mathematics to this day, I think. All right, they have this proof of that one in here, so I want to read that part. It's really, really nice. That's it.